Good morning, Calculus 2 students. Again, we're enjoying the cool weather, and I'll never have an issue with that. I guess now that I live in Texas, I can appreciate the cool weather because we mainly have warm weather, which again, I'm not complaining about. I enjoy the warm weather, and it's always usually beautiful in this area as long as it's not raining, but we need the rain too. Now, what we want to do today is go ahead and look at the next topic in chapter 7, which has to do with measuring the length of a curve and then taking a curve and rotating it as opposed to a region to create a surface, and then figure out how to find the area of the surface. So we're just going to take the same type of construct that we've been working with, but just focus, excuse me, on the boundary and see what that gives us. Now, before I do that, there was one of your classmates had a question about a washer method, and I shared a solution with the classmate, and I just wanted to share that with everybody. This is in section 2, and this is similar to some of the problems that I've done in class. And what I thought was interesting about it is that for the second part, as opposed to just rotating this region here, and if you want, I put in the rectangle, you can just go ahead and shade this. This is a nice symmetric region with two quadratic functions. And the idea is part B said, well, take this region and rotate it about y equals 10. So of course, that's going to, again, use the washer method because in either case, the region does not completely abut the axis of revolution. So the only thing about this problem that I noticed when I responded to the WebAssign message is that it had a little bit more arithmetic in the expansion of the binomial. So for here, the outer radius or the larger radius would just be 10 minus the lower curve, which is the x squared curve. And then the upper curve here will help us to form the smaller radius or inner radius, which will be 10 minus 6x minus x squared, of course, distributing the negative sign to get this for our expression for r. And so now, I mentioned in the message that I sent that it was fairly straightforward from here on out, but if you look in my lecture notes, you'll see a problem similar to this. When you have the outer radius squared minus the inner radius, of course, multiplied by pi. And then of course you could set the two curves equal to find the intersection like we've done many times in class to get the interval of integration. And at least in this particular problem, everything else is pretty straightforward, but in this particular problem, the lower limit is 0. So that's always a plus when we have to do our work. But I just wanted to remind you, when you square this binomial, that's something we've done a million times. But when you do the trinomial, it's the same type of formula, but when I looked at this, I thought, okay, well, let me just remind everybody about it. You square every term as you normally do, like we do here. We get the 100, the 36x squared, and the x to the 4th. And then in pairs of 2, you multiply them and hit them with a 2, just like you do with the binomial. But you multiply these two terms together and hit it with a 2, you get negative 120x. And now you can multiply the outer two terms, 10 times x squared times 2, 20x squared. And then for the last two, you can say negative 6x times x squared times 2, which is a negative 12x cubed. So that's the only kind of kink in the problem, but it's not a difficult one. You can always multiply it out. And then you can see after this, it's just, what is it we do in Calculus 2? We do a whole lot of arithmetic. The issue, and this is what you saw when you took pre-cal, it's like, gosh, you got to do all this algebra and all this fractional arithmetic. It never ends. Well, now it's like we're in pre-calculus again. So at this part, I'll just summarize this. This is what I've done in class a million times, in the sense that we just collect all the terms, and then we've just got add 1, divide by the new power. And notice here, I extract the 4 here to make the number smaller, and then I run it back through to kill the 4 that we get here when we integrate this particular function. And so you can see that at this point, it's just a straightforward calculation. But again, just remember, as you're working these problems, the sketch gives you kind of the essence of the problem, in the sense that it orients everything so you can see, have the visual on the outer and the inner radius. So there is indeed a visual component to these problems, whereas you could probably think in your mind's eye and say, okay, that's what this is and that's what this is, but it's better to go ahead and have a little diagram. And what I like about the WebAssign is that it kind of keys you into that to kind of help you along your way. So this was just a little extra that I wanted to share with you, because I thought the question was a valid question and a good question to share with everybody. Okay, so what we want to do now, again, is talk about lengths of curves. So when you think about the length of a curve, at least a line segment, you know, that's just a plain old Euclidean distance. That's just the right triangle, Pythagorean theorem. And, you know, so we're thinking, can we take that construct and apply it to general curves? And the answer is yes. But the integral we get is not the most user-friendly, but that's okay. We will survive. So we're going to start off with 7.4, and we're going to entitle this arc length. Now, instead of saying function length or something like that, let me adjust this a little bit so it's nice and aligned. Instead of saying like function length, we think of the function graph as being a curve, or maybe it's not necessarily defining a function because it doesn't pass the definition of function with the vertical line test. So we replace function or curve with arc. So the arc could be anything. It could be a functional graph, or it could just be a curve in general. And so that's where the word arc comes from. So don't be puzzled by that. So we'll just say length of a curve. And so the curve could be given by an equation or a functional equation, depending on what we have. And let me grab the focus there, make sure that's nice and sharp for you. And then we're going to do a surface area. So we'll say area of surface of revolution. That's a little bit easier, and that deals with the frustum. And that's something you've probably seen before. It's like the waste paper basket. It's like a cone that's been chopped off. And so we'll talk about that. So again, we're going to get a nice little geometric way to get a formula for this, just like we got the formula for the shell method. You know, sometimes simplicity is the best way to go. And we're finding that our knowledge of high school geometry has really paid off. So for instance, say we have, and I'll set this up, this is very straightforward, and it will remind you of the derivation we did last time. So I want to keep this very intuitive, and then we'll jump to the partition just like we did in the last couple of times. So say, for instance, we have an interval of integration A to B and a curve. Just say we'll just draw a curve here. So say it starts here and goes somewhere like this, all right? So that would be our curve. We could call that F. If you want, we can call our curve F. It is, I've drawn it so it's a function. And so what we want to do is take an interval. We want to partition this particular interval and look at a subinterval. So let's do that. And then, of course, we'll add this up over the entire partition and let the norm go to 0. So say we have our x sub I minus 1 and our x sub I. That's the I sub interval. And so now what we want to do is just draw in our curve for that little piece. Say the curve looks something like this at that piece. And so what we're going to do is we're going to use the hypotenuse of a right triangle to approximate the length of this. But what we're going to find is that as the subintervals get smaller and smaller, that approximation will be exact. So in the limit, that's what we're looking for. So we use simple ideas and then take the limit of the Riemann sum to produce an integral. And we keep our fingers crossed that it's an integral that we can work on. So now what we can do is form a right triangle. So again, we have this partition. I'll just go ahead and write it out in red. It's kind of important. So x sub 0 is our left endpoint, A, and then we'll have an x1. And then, of course, we'll have x sub I minus 1, x sub I, and I'll keep going. And I'll finish here, and we'll end up with the very last element of the partition, which is B. So what we're doing is focusing on the idea that if we can look at one subinterval and get a nice relation for the length or an approximation of the length of this piece of the curve, then we can apply that to the rest of the subintervals, add it up, and then take the limit. So the idea is exactly what we've been doing. So none of this has changed. So let's go ahead and draw in the legs of the right triangle. And then, of course, here we'll have x sub I minus x sub I minus 1. And we can just call that, if you like, delta x sub I. By definition, the length of any subinterval is non-negative, okay? And so we'll use the notation we normally use with the partitions. And now here, what we're going to do is look at the difference between the functional values. So this will be f of x sub I minus f of x sub I minus 1. So the only reason I'm using the partition here is because it's real easy to see. And I want to make sure this is not too light so you can see the red. Yeah, not too dark, but there we go. That looks a little bit better. That way you can see the red. Excellent. Okay. Good old IPEVO. All of my colleagues want this IPEVO document cam now. And I said, well, it's a good instrument to use. The virtual is here to stay. So we're going to do face-to-face when we can get back to campus and still continue to do virtual. So we'll have many modes of teaching at San Jac. I guess all over the world, this mode will be part of the education process. Now, what you can see here is that we've got lengths here, and it wouldn't matter if this were increasing or decreasing. We're going to square everything, so there won't be an issue with sign that we'll actually get something that'll work. So now we can say, if you like, and I'll do this in blue, we'll just dot in the hypotenuse, and I'm going to call that delta S sub I. We use lowercase s for arc length. So that's going to be the hypotenuse of the right triangle. So this will imply, just by using the Pythagorean theorem. So now we're back to general math, which is important math. We do general math all the time. So we'll say delta S sub I squared will now be the sum of the squares of the legs. So we'll say delta x sub I quantity squared plus f of x sub I minus f of x sub I minus 1 all squared. So again, it doesn't matter here since we're squaring this. If the roles were reversed, no problem. So squaring is a good thing to do to keep track of signs. So now at this point, this is kind of like what we did with the shell volume. We took the difference between two cylinders, one cylinder living inside the other, and that created the shell. So we look at this and say, okay, well, we've done that part. So what's the basis now for what we need to do? Well, we want to factor this and then use the mean value theorem from calculus 1 to get a better expression, something that we can use. Now, another thing that I haven't said, we're going to assume that this curve is what they call C1. That means that the first derivative is continuous. So we will assume, we'll just say assume that f prime is continuous on AB. When we get to Taylor's theorem, we're gonna call it Cn. And so, or C, we're going to need that many derivatives to be continuous. Well, so for now, our formula is going to require this. So that's a little hypothesis that we can go ahead and add now. That is, when we take the derivative, we get a nice function on this particular interval. So what we want to do now is factor the delta x sub I. So this will leave us here with a 1. And then we'll have the f, and I'm going to go ahead and do the square on the outside of the fraction. We'll have a square divided by a square, so I'm just going to use parentheses and square on the outside, just to make this a little bit neater. So of course, if we divide, or if we factor the x sub I squared, we have to pay for it here. So when we multiply back through, this absorbs and we get exactly that. So now what we can do is just square the whole thing. So we're looking at this and saying, well, this isn't half bad because that is just basically a difference quotient. That's the mean value theorem, the rise over the run. And so there's some C sub I in this interval here, and we can just go ahead and mark it in if you like. We really don't know where it's going to live, but we know it exists, that so that we can write this actual difference quotient as the derivative. So the thing that's interesting about this, when we write it this way, we can now move to the mean value theorem. And so that's why we need that particular apparatus. So now I'll say mean value theorem, MVT. I'm sure you did spend a lot of time with this, or your professor talked a lot about the mean value theorem. Very important result. So we get 1 plus, and now we can replace this with the derivative, f prime C sub I. And of course, this is squared now. So now we can look at this and say, okay, well, if we're going to do an arc length problem, then we're going to take a derivative and square it and add 1. And then, but now we're like, okay, well, so how do we kind of finish this off? It looks like we're almost to the finish line, but we don't need the square of the length. We need the square root. So now what we can do is apply the principal square root. So I'll say apply principal square root. I mean, we don't need the square of the length. We just want the actual length. So when we do that, we can take the square root of this. So this will be the square root of delta S sub I squared. But again, that's the absolute value of delta S sub I, but delta S sub I is a non-negative quantity. So we can just replace this with delta S sub I. So we can say here, the absolute value of delta F sub I is itself delta S sub I. And then again, since the length of the subinterval along the x-axis is also positive, when we take its absolute value, we still get the term itself, because by definition, these quantities are non-negative. So that simplifies things. So now what do we get? Well, this equals, so we have the square root of delta x sub I squared. So that's what this is going to be, and we'll be able to replace that with this. Because, I mean, if you like, we can go ahead and just go ahead and do this, just to remind you that this is an alternate definition. I mean, this is easy, but you know, sometimes it's good just to remind yourself what you're doing. And then, of course, here, I'll use the brackets. We get 1 plus f prime c sub I squared to the 1/2. And that we can't really reduce. That's the kind of the thorn on our side here. So now we see we have the length for each ith subinterval. So this is 4 for x element x sub I minus 1, x sub I, and then of course c sub I lives in there too. So what we want to do is take this construct and use it for every subinterval. The same thing, add it up and take the limit. So this gives us our definition. So now we will say, and we'll use the lowercase s for arc length. Lowercase s will now be the limit as the norm of the partition goes to 0. That is the lengths decrease to 0 of each subinterval. The largest subinterval squeezes down to 0 in length, and that drags everything else. And so we have this, I equals 1 to n here. And if you like, we'll go ahead and replace this with the delta x sub I. F prime c sub I squared. Now, if you like, you can go ahead and put brackets here if that makes it a little easier. I was a little sloppy there just with the square, but go ahead and put in the brackets or the parentheses. And now in the limit, this becomes the dx, and this just becomes the x. And then, of course, we're integrating here from a to b. So we have a to b, and we'll use this with the area of a surface that will have an element of arc length, so to speak. And we can use square root now if you like. Sometimes we just use y for f to shorten the notation. And so this gives us a nice, I mean, the idea here is that this is just like what we did before, and it's worth going through. So now you can say, okay, in general, when we want to find the length of a curve, it's still Pythagorean. Just like finding the length of a line segment, we use the Pythagorean theorem, which is Euclidean distance. But then, of course, when we generalize to a curve, of course, we like it to be differentiable. And then, of course, f prime to even also be continuous so that it makes sense to try to integrate this. We know functions that are continuous are Riemann integrable. And that's useful. That's a big result from Calculus 1. And so even though there might be times when this would be a hard calculation to do, we will work problems where this integral will actually compute by methods that you understand. And then of course, if you were in a physics class or an engineering class, you might get an integral where you would have to approximate it using Simpson's rule, but that's fine. I mean, you can approximate to any level of accuracy if you just need 2 decimals or whatever to finish your model. So again, not the most user-friendly integral, but at least a formula that we can use. And then of course, when you get to the end of this course, we'll generalize this again. And when you get to calculus 3, you'll generalize this for curves in 3 space. So more differential geometry, where you'll take this and just basically generalize it. So we set a lot of the groundwork for future work in mathematics in Cal 1 and Cal 2. So it prepares you for Cal 3, differential equations, linear algebra, topology, more analysis, complex variables. The list goes on and on. Calculus is like the bedrock. So let's use this formula. Now, when we think about doing a calculation, let's start with something that is memorable to us. That uses some calculations from calculus 1. And here's the following. We'll get some review with some logarithms, and then that'll make you feel good that you haven't forgotten them completely. So like I say, with these examples, we'll have a formula that will allow us to move forward with the integration. We won't just stop and say, okay, well, I'm going to have to use Simpson's rule. So we're going to have y. Our curve will be the natural log of cosine of x. Now that looks a little bit odd, but it will be a function that we can actually integrate with our arc length formula. So we have an interval of integration, which is 0 to pi over 3. So first we note that this is actually going to make sense. The cosine function is positive here, and so the argument of the natural log makes sense. This is defined. We certainly don't want to compute the length of a curve when it doesn't even exist. So this is fine. Again, always check to make sure as we work through these problems, don't just assume they make sense, check it out. And what we want to do is compute the arc length, or just compute the length of the curve. And we want to use our formulation from the last derivation. And then we're gonna go back and review some of your integrals from Cal 1 that may be a little rusty. Remember, I sent you that PDF. I appended 4 end papers from the textbook. It has that basic list of integrals, the 1 through 20, that includes the inverse trig forms. That's a good thing to have as a reference. You might just want to print that out because, like I say, one of your classmates clued me into the fact, he was basically saying, what can I review? And then when I found these end papers, they really weren't a part of the ebook. So have that available. It has a lot of nice geometry and just a lot of nice facts about trigonometry and basic calculus that will always be useful to you. So let's just break this down with the recipe. First, we want to look at y prime. So remember, when we compute the derivative of a log function, we reciprocate the argument. So that means we reciprocate cosine. And then we multiply by the derivative of the argument, which is negative sine. So again, when we differentiate a log, we reciprocate the argument, and by the chain rule, multiply by its derivative. But of course, now this is sine over cosine with a negative. So it probably is of no issue to go ahead and write this as negative tangent x. Lots of times when you're doing work, you think, well, should I write it in this form or should I write it in that form? As we work through a problem, we may go back and say, well, this form will be a little bit easier to work with because I know this formula in this particular form. So again, don't worry if you go back and forth between ideas. If it's correct, it's correct. You're just trying to make the flow of the problem easier. Now, remember the formula says that we need 1 plus y squared. So now 1, and this is where it's nice to use the prime notation and not worry about the independent variable. It's a little bit easier to write. So this is like the 1 plus f prime squared. So we do 1 plus y prime squared. So this will be 1 plus negative tangent squared. Of course, the negative will absorb, and this gives us, let me move the mouse over a little bit. This will give us 1 plus tangent squared x. But of course, that's one of our Pythagorean identities. This is just secant squared. This is just a fundamental identity that, we divide by cosine squared and get a Pythagorean identity. Okay, so now this gives us the radicand, or the argument of the radical, for the arc length formula. So now this implies that our arc length, again, we use lowercase s for area of a surface, we'll use uppercase. Don't ask me why that's something that's just kind of been passed down through the ages, good or bad. You can just write out arc length, but you will see the lowercase s and uppercase s in your WebAssign in your book. So now we can say, all right, well, we have the integral from 0 to pi over 3. So it's like doing the ladder problems, lots of arithmetic, and we have the square root of 1 plus y prime squared, which we've computed to be secant squared. And so now we're kind of back to the derivation. We have the square root of the square, which is the absolute value. But then, of course, we know where x lives, just like we know the cosine. And so on this particular interval, the secant is positive since the cosine is positive. So we can remove the absolute values. And so now we're back to calculus 1. Remember when we did the du over u? This is by Lagrange. So the antiderivative, and you can look on your basic form, is the natural log of the absolute value of secant plus tangent. So now we've got a calculus 1 integral, du over u. So we have the natural log secant x plus tangent x. And we'll integrate from 0 to pi over 3. So again, this is calculus 1. Our calculus 1 problem. That didn't even look like a, sorry, let me make that a little clearer. There we go, calculus 1. That looks a little better. So again, use your reference chart for this. And now we can use the fundamental theorem. So we have natural log secant of pi over 3 plus tangent pi over 3. Use parentheses just to make things clear. A lot of times we leave them out, but use parentheses as you need. And then we have natural log secant of 0 plus tangent of 0. So again, if the curves look a little bit odd, it's basically because we want to provide curves that will give you an antiderivative when you do the actual integral. And so now we can substitute or use our unit circle. So we have natural log. Of course, secant of pi over 3, that's 1 over cosine of pi over 3. That would be 2. So we have 2. And now, of course, the tangent of pi over 3, that's just where we have sine over cosine. So that's square root of 3, just from your unit circle. And I think on those cards, there's a unit circle that gives you values for that that will be useful. And then, of course, the secant of 0, that's cosine of 0, basically. That's 1. And, of course, tangent of 0 is 0. So now we can't reduce this. So we have natural log, and we can just use parentheses. That's a positive argument if you like. Use the absolute values if you want, no difference. And then, of course, we have log of 1. And log of 1 is of course, 0. So we get an answer, natural log 2 plus root 3. Now, the idea here, again, is we don't really have what you would see as for instance, I mean, we do have basically, let me reverse that. We do have a construct that reminds us of what we've done before. That is, we apply some basic geometry, then attach the calculus to it, like we did here. We apply some basic geometry, Pythagorean theorem. Then we attach some calculus to it. So that's really been the rule of thumb for this chapter. You know, we're not really learning any new math. We're just taking the math we know and synthesizing it in ways to give us new ideas, to give us new definitions. So this, ladies and gentlemen, will be ideas that you can apply all over. I mean, calculus is universal, but these will be things that you will actually use quite a bit in physics and engineering. Now, let's look at another example. Got several examples here. The next one has to do with maybe a more algebraic spin, and then we'll talk about surface area, and then maybe do the area of a roof. That there's a nice Webasine problem dealing with some hyperbolic functions. And again, if you didn't study a lot of the hyperbolic functions before, it's not hard. The relationships are easy. They have nice simple formulas. Now let's do another example of the arc length so you can see the algebra at work. Let's face it. When it comes to doing these problems, you can think of a real simple curve that you know, and you can apply this formula, and you won't get an integral that you know how to do. You're thinking, well, I'm going to have to wait for Professor Ron to show us this technique. So again, the square root is really a thorn in your side when it comes to actually getting an antiderivative. So let's look at another curve. We have y equals x to the fourth divided by, in this case, well, you see what the answer is going to be. It's going to be kind of crazy. So I saved this one a little bit later so we can do the arithmetic. So we have x to the fourth over 8 plus 1/4 x to the minus 2. I like it when I prepare these examples, I'll say, oh no, the kids are going to be like, oh, we got all these fractions again. Well, you know, that's calculus. If someone ever asks you what calculus is, you can just say it's fancy arithmetic, because that's pretty much what we do. And so what we want to do here is compute arc length. So when you look at this example, you know, you have to look at it and think, well, keep your fingers crossed that we'll maybe get a perfect square. And so when we square root it, we'll get the power rule. So with these examples, just like the last one, you work through it and then, you know, focus on the fact that you'll actually end up with an integrand that you can work with. So this kind of like, if I asked you to do something on a quiz or the first test, which comes up next week, and I'll have more information about that on Blackboard. If I ask you to do arc length, it'll be something that you can integrate. So you don't have to worry about bringing out the approximate integration. So one thing that we can do that you notice here, this is in good form to differentiate. So first thing we're going to do is y prime, take the derivative. So we're going to have 4 over 8 x to the third, just using the basic power rule. And then plus, we'll bring the negative 2 over 4 x to the negative 3. Okay, so let's reduce that a little. This will give us 1/2 x cubed minus 1/2 x to the negative 3. And then, of course, if you like, we can factor the 1/2. You'll never be remiss to factor. You can always reverse it. It's okay, not a problem. So that's the derivative. So again, we always assume that we can actually compute the derivative, and this certainly is continuous on that interval. So this is a C1 function. So now we want to square this and add 1. So 1 plus y prime squared. So we want to square this. So let's just go ahead and use a bracket. So we square the derivative. So now we have 1. And of course, if we square the 1/2, we get 1/4. And now our friend squaring the binomial, what we do all the time. So again, x cubed squared will be x to the 6th. Now we multiply, but notice these are just reciprocals. So this is x to the 3rd times 1 over x to the 3rd with a minus. So that'll be a -1 times a 2. So that's a -2. So again, these are reciprocals. And then we want to square this. So we get plus x to the -6. So again, the binomial squaring that you did in pre-cal is extremely important. So we use that here. So be very careful when you do this. If you want to write that as a fraction, it might be easier to see. But again, these absorb to give you -1, hit it with a 2. Now, of course, we can get a common denominator. So we'll have a 1/4. Go ahead and factor the 1/4 throughout. And of course, that means we multiply the 1 by 4. So we have 4 plus x to the 6th minus 2 plus x to the -6. So again, we have the 1/4. And if you like, you can write this in descending order like we're trying to do. So x to the 6th. And then, of course, we have the 4 minus the 2. So that's plus a 2 plus x to the -6. Now, when you look at this and you're thinking, well, this is kind of like going backwards, we get another perfect square here. That is, we've got the x cubed, x to the -3, and then the product times 2, which gives us 2. So this is a perfect square. So you want to look for the perfect square when you have these algebraic type curves, okay? So now this will be 1/4 x cubed. So it's like we're going forwards to go backwards, plus x to the -3 quantity squared. So this is a perfect square. So really simple algebra, but important algebra. So again, you look at these problems as being set up so that the curves are actually fairly interesting. Of course, this has a vertical asymptote at 0, but we're well away from that. So these are really interesting curves, but bona fide curves that have all the nice attributes that we want them to have. So now this will imply that we can now set up the interval or integral for the arc length. So this implies that S arc length will now be the integral 2 to 3. Well, we don't have a lower limit of 0, so all that fun is gone. So we have 2 to 3, and then we'll take the square root. I'll use brackets 1/4 x cubed plus x to the negative 3 squared 1/2 dx. So again, you don't have to go ahead and write, 1 plus y prime squared or whatever. We kind of see that that's what we have here. And then of course the formula says we need to take the principal square root of this. And so now we're thinking, okay, we're good to go. So this, when we take the square root, 2 to 3, of course the square root of 1/4 is 1/2. And then of course we're taking the square root of the square, so that gives us the absolute value of x cubed plus x to the minus 3. But again, on this particular interval here, these are positive quantities, so we can remove the absolute value. So now we just have 1/2, and you can go ahead and factor the 1/2 here, just using linearity of the Riemann integral. So like on the first test, I'll have you turn in your work so I see your work and maybe not give you too many problems. I'm probably going to set up a Blackboard test so you can work out everything and then turn in your work, choose the correct answer or the best answer, and that way you have an opportunity to show me your work, which is important. So now when you look at this, you're thinking, okay, well, we just add 1 divided by the new power. So this is back to calculus 1. So we get 1/2. And so we have x to the 4th over 4. And now we add 1. So we have plus x to the negative 2 divided by negative 2. So again, when we add 1 to the negative 3, we get negative 2 divided by the new power. And we want to integrate, in this particular case, from 2 to 3. So to make this a little bit more user-friendly, we'll do 1/2 x to the 4th over 4 minus the negative here, 1/2 times 1 over x squared. That just puts it in a form that might be a little bit easier to evaluate, okay? So now we've got something that looks fairly reasonable. And so now this is just calculus 1 fundamental theorem. So let's work it out. So we've got our 1/2. Now first, what we want to do is substitute the 3. So we have 3 to the 4th over 4 minus 1/2. Now, of course, we have 1 over 3 squared. So again, substitute 3 to the 4th over 4, the 1/2 is factored, minus 1/2, 1 over 3 squared, and now substitute 2. So we get 2 to the 4th over 4 minus 1/2 times 1 over 2 squared. So again, we have to be court reporters, but good court reporters. So now when we look at this, we've got basically 9 times 9, so that's 81 over 4. Minus, and now of course here we have 2 times the 9. And at this point, notice that the 2 to the 4th, 4 is just 2 squared, so we can say 2 to the 4th over 2 squared is just 2 squared, or 4. So that's basically 16 divided by 4. So this is just a 4. And then we have minus 1/8, 2 times 2 squared. Now we want to go ahead and distribute everything. Let me move this up a little bit. So we have 1/2, 81/4. And now we have minus, I'll just leave that alone so we can do our common denominator. And now we have -4, and then minus minus plus 1/8. So at this point, what you can do, again, we're good to go with all of this. Notice we need a 9 and we need an 8. And then of course here we need a 2 and a 4, and that's just 8. So our common denominator would include the 9 and the 8. So let's go ahead and write that. So we'll have 1/2 So we'll do 9 times 8. Now notice with the 4 here, this is going to give us a 2 times a 9, which is an 18. So this will be an 81, or an 18 times an 81. And I'm going to be careful how I write this. I'm going to write this as 80 plus 1, so it's easier to multiply. So again, 4 into here will leave us a 2. 2 times a 9, which is 18, times 81. Now, of course, here we've got the 9 and we've got the 2, but that we don't have the 4 from the 8. So this will be -4. And then here we don't have anything. So we get -4 times a 72, 9 times 8. And then the very last one, we have an 8, but we don't have the 9, so we get plus a 9. So let me move this to the next set of papers. So at this point, the algebra is fairly simple, but we just want to combine the numbers and see what we get, and see if we get that ugly fraction that I said we're going to get. So we have 1/2. And now if we notice here, if you like, we can go ahead. Let me just go ahead and write this out here. Just get it out of the way so it's easier to see. Go ahead and bring out that 72. Just write it out here. That way we don't have to keep writing the fraction bar. And so now we can look at this. We get an 18. And then here, and let me move this down so you can see it. So we get the 8 times the 8, that'll be a 4. And then the 8 times the 1 plus the 6 will be 14. Then the 0. So this is what I was talking about. When you actually break down the numbers, it's easier to multiply and it's easier to go back and check. And then of course we have a -4. And now of course here, this is easy to multiply. So that'll be an 8. And then of course a 28. So 288 plus a 9. So now we've got a 1 times a 2 times a 72. That's going to be a 144. And now at this point, what we can do is just add the numbers that are simple. Notice here, we can add the 18. So that's going to give us an 8. And then the 5. So 1458. And then we have plus the 9. Now here, of course, we can add these numbers. That'll just give us a -292. Now, when you look at what we've done here, the next simplest thing to do, again, if you want to, is go ahead and add these two numbers and then subtract. I always think about ways to simplify arithmetic, but now this will be a 17 with a 1, 6, 4, and a 1, minus 292. So that's about as simple as I can make it. And so now when we subtract 2 from 7 is 5. And then we have the 16 minus the 9, which will give us the 7. And then we have the 13. So the 3 minus the 2 will be the 1. And then the 1 we didn't borrow. So we actually got what I computed. So this is kind of what I was talking about before. The work here involved is very arithmetic. And it's important to be able to work through the calculation and say, okay, does any of this make sense? Well, first, we got a positive number, and length is non-negative. So that's another plus. And again, we start with a calculation where we look at this and say, okay, we've got an interesting curve. Professor Ron says this is set up so we'll get something we can integrate. We get a perfect square. And then we apply the principal square root here. And then we just basically have add 1, divide by the new power. But the arithmetic is more complicated just because of the fact that we have a lower limit, which is non-zero. We depend on that sometimes, but I want you to see that as you work through this, this is just basic arithmetic. That's what calculus is, fancy arithmetic, and we're able to reduce it down to some fairly simple numbers. I think one thing that's interesting about the calculation here is, and I teach my pre-calculus students to do this, always break down numbers to smaller numbers. That way you can actually do the work linearly, and then you can go back and check. And so now we break these down to numbers that are easily to do pairwise. So this is really an exercise in arithmetic, but it's important arithmetic. So when you think about limits, that's arithmetic. You think about derivatives, Riemann sums, all arithmetic. Okay, so I wanted you to see that all of the problems you have in your WebAssign will always turn out to give you a nice integrand that you can actually integrate. Now, I want to do an example. Let's see, where did this one go? Here's a good example of a calculation that I think might be useful to you. And let's see. Yeah, here we go. It's the one that talks about the roof. Now, I want to just give you a little refresher with hyperbolics. I don't want you to get to this and say, well, I don't know what I'm doing, Professor Ron. So as we get to it, I'll mention, but let me just make a couple of notes here. I'll just say, recall, and I know some of you talked about this in your Calculus 1 class, we have the hyperbolic functions. Now, these have to be derived with more complicated means, but the hyperbolic cosine is actually expressed in terms of natural exponentials when you solve the differential equation. So you actually get e to the x plus e to the negative x. This is what you do at the end of Calculus 1. So what's nice about hyperbolics is that we actually get some fairly simple derivative and integral formulas because we have a cogent formula here, unlike the standard trig functions, which are abstractions of the unit circle that don't give us these nice formulas. So this is an improvement. And the hyperbolic sign is e to the x minus e to the negative x divided by 2. And these have many of the same attributes that the standard trig functions have. And there's another thing that I wanted to write down. I'll just say in this case, here's the fundamental identity. When we square the hyperbolic cosine and we subtract the square of the hyperbolic sine, we get 1. So the fundamental identity is a little bit different. Instead of the plus, we get the minus. And just to kind of remind you here, the derivative of cosh, or the hyperbolic sine, is the hyperbolic, excuse me, the derivative of the hyperbolic cosine is the hyperbolic sine. And of course, these can be extended by the chain rule. You don't get the negative. And then, of course, well, of course, I don't know if it's of course, the derivative of the hyperbolic sine is the hyperbolic cosine. So you don't get any negatives floating around. So I just wanted to give you that. And then, of course, you can take ratios and define hyperbolic tangent. So hyperbolic tangent would be the ratio of hyperbolic sine to hyperbolic cosine. So in continuing, you could just say hyperbolic, and you can do hyperbolic cotangent. Will just be the sine to the cosine, and of course the 2's go away, and you get e to the x minus e to the negative x divided by e to the x plus e to the negative x. So you get some really simple formulas that can be manipulated with the calculus, because you know the calculus of the natural exponential. So this is just kind of a, you can spend a lot of time on the inverse hyperbolics, which I do in Calculus 1, but these are formulas and functions that turn up a lot in engineering and physics. So you're thinking, do we have to spend a lot of time on these in this class? Not necessarily, because there are other means that we can use when it comes to certain integrals. But there are times when students just defer to these, and that's fine. I mean, good math is good math. So what we have here, and so that's kind of a little bit of review of that. Here's an example. We have the cross section of a roof is an inverted quaternary. So this, the shape of this function is called the quaternary, in the sense that if you suspend a power line between two poles, so you've got these poles here, and you suspend a power line between them. The shape is a quaternary. That shape right there is what we call a quaternary. I'll spell it for you. Quaternary. And the shape of this is the graph of the hyperbolic cosine. So this corresponds to the graph of hyperbolic cosine. That's called the quaternary. And so in this particular problem, they say that the roof of the barn is an inverted quaternary, so it slopes this way. So in this case, the cross section of the barn roof is an inverted quaternary. And they give you a formula for it. Quaternary. And here's the formula. This is where you use a little bit of your college algebra. So we have y equals 31 minus 10 times e to the x over 20 plus e to the negative x over 20. And so when you look at this, you see how it mimics this. X has just been replaced with x over 20. So this is the hyperbolic cosine. And here's what we have. It says determine the area of the roof, and I'll draw the picture from WebAssign. So determine, we're going to do an arc length calculation and then just multiply by the breadth of the roof. So determine the area of the roof. And so the way it's written, there's a nice little diagram here in your WebAssign. So this makes a nice arc length problem. And so we'll mark off negative 20 and 20. So that's where these 20s are coming from. So we have the inverted quaternary. Kind of looks ellipsoidal, but not quite. Like that. And then we can just run the breadth back. Like that. And this distance here is 100. And in this case, this it may be feet or whatever, but that's not important. The dimension is okay, feet or meters or whatever. And what we need to do is to compute the length, arc length of the quaternary, and then just multiply by the breadth. So once we have the length of this curve, we can multiply by 100 to get the actual area of this roof. And of course, the idea here is when we work with arc lengths, we take the generalized notion that we've been using for the last problems. So here's the key. Compute arc length of y, again, on negative 20 to 20, multiply result by 100. And this gives you the area that you need. So now what we can do here is just manipulate this. And of course, even if you don't recognize these formulas here, you still know how to do the calculus of the exponential that you learned in Calculus 1. So let's do the derivative first. So now the derivative of 31, of course, is 0. And so we have minus 10. And so now we'll have e to the x over 20 times 1 over 20. That is the derivative of the power, plus e to the negative x over 20 times negative 1 over 20. So we know that's just the hyperbolic sign, but that's neither here nor there. So now we have y prime. And if you like, you can go ahead and factor the 20 in this case. So we have negative 10 over 20. And this leaves us with e to the x over 20 minus e to the negative x over 20. So again, when you look at these calculations and you think about what you have, it's just like we did in the previous problems. And now, of course, we can reduce this to a negative 1/2. And of course, those derivative formulas give us nice integral formulas too that are simple. So now we see that we have the derivative, and now we want to say 1 plus y prime squared. So 1 plus y prime squared. So I was telling you before, this formula presents a lot of algebra just by its very nature being Pythagorean. So we get 1 plus, so let's square it out. So we have negative 1/2. So we're going to square binomial again, e x over 20 minus e to the negative x over 20 quantity squared. So this gives us 1 plus, now of course we square the negative 1/2 to give us 1/4. And now of course we square the binomial. So we multiply this by the 2, the power of course that will absorb in the 20. So we get e to the x over 10. And now of course, just like we saw before, these are reciprocals. These are reciprocals. We get -1 and hit that with a 2. So -2 seems like what we just did. And now, of course, we square this, but of course, we retire the 20 to the 10 because of the 2. So we get plus e to the negative x over 10. So when you look at these calculations and you think about what we're doing, this reminds us exactly what we did in the previous problem. So now we can get a common denominator. So that's why I did this problem before, to kind of give you a reason as to how we'll work on this one. And so we'll factor the 1/4, pay for it here. So that gives us a 4 plus e x over 10 minus 2 plus e negative x over 10. So now we have a 1/4, and so we can combine and just write in a descending order, if you like, e to the x over 10 plus 2 plus e to the negative x over 10. Now, of course, this is the same situation we were in before. When you think about this and you look at this particular problem, we've got the perfect square again. That is, this, even though it's a little bit harder to see, we're going to go right back to that denominator of 20, perfect square. And I'll write this below so you can see it. So this is going to be 1/4. And now we'll have e to the x over 20, because when we square that, the 2 is retired to give us this. And then plus e to the negative x over 20. When we square that, the 2 is retired, we get this. And then, of course, these are reciprocals. Hit it with a 2, we get that. So it's like we go forwards to go backwards. But now, look, this is giving us exactly this function. That's why I wrote these down. So now you can bring the 4 in and square root it. So we get e x over 20 plus e negative x over 20 divided by 2 quantity squared. But this is where you see, and we'll do the arithmetic with the formula, but you see this is just the square of the hyperbolic cosine, where x has been replaced with x over 20. So you can allude to that to make the calculation of the integral easier. So now let's finish this off. So unfortunately, the arc-length problems don't present simple integrals, just because of the fact that we want you to actually get something you can integrate. Now later on, we'll be able to change things a little bit, where some of the integrals will be easy to set up, but you'll have the methods to actually compute them. So we'll do more of those. So now let's go ahead and apply the definition of arc length. So this implies, so we're going to see basically, what's the length of that curve right there? The inverted quaternary. So now S will be the integral. You're thinking we can use symmetry, but let's just go ahead and work it out. I've thrown enough at you as it is. -20 to 20. And we have the principal square root, I'll just use the brackets, e to the x over 20 plus e to the negative x over 20 divided by 2, quantity squared to the 1/2. Now, of course, this is the principal square root of a square, so we get the absolute value. E to the x over 20 plus e to the negative x over 20 divided by 2. But now, of course, on this particular interval here, the function is non-negative. It's the inverted quaternary, and so we can remove the absolute values. So in this case, we can go ahead and replace this with cosh if you want, or just leave it alone. So this is going to be e to the x over 20. Well, I'll make the replacement once I do this. So now when we look at this, like I said before, this is just the hyperbolic cosine where x has been replaced with x over 20. So now let's just go ahead and write it that way. And then we can use our calculus to finish it off. Of course, it's an even function. Hyperbolic cosine x over 20 dx. But now, from our calculus here, the integral of the hyperbolic cosine will be the hyperbolic sine if we just work this backwards. So now we can use this calculus. So if you want to write in your notes, this implies that the integral of the hyperbolic cosine is the hyperbolic sine. So that just simplifies things a little bit. So there's a whole lot of stuff going on here, not overly complicated, but just kind of like, okay, hyperbolic functions, here's how we work with them. So now, when you look at this, we just have make this table ready. So we have u equals x over 20. So du is 1/20th dx. So we need the 1/20th dx. We only have the dx, and then we'll pay for it. So this will be 1/20th negative 20 to 20 hyperbolic cosine of x over 20. And then, of course, we'll have the 1/20 dx. This is table ready. Now, this is where you say, well, Professor Ron, are you just gonna write it out as it is? And I will. This is an even function, so we could just integrate from 0 to 20, and then do it that way. But I want to give you practice using the formula. So I'm gonna make it a little bit more time consuming just to give you practice with the formulas. So now, oh, of course, 1/20, that needs to be a 20 because I've got a fraction inside. Good old arithmetic, right? So we got a 20 there. So we have to kill that, okay? Normally it's just the opposite. So now, using this formula, we have the hyperbolic sine, and then we know the formula for it, and we can fill it in. So that'll give us practice using the formula. So now this will give us 20 hyperbolic sine x over 20 evaluated from negative 20 to 20. Now, of course, the hyperbolic sine, that's the e. We'll put in all the e's. So this is 20. So we have e to the x over 20 minus e to the negative x over 20 divided by 2, just filling in the formula for the hyperbolic sine so we can get a number devoid of hyperbolic sine. Negative 20, 20. So now we have 20. If you want to factor the 2, we can. So we have E. Again, let's substitute the 20. So the 20 is absorbed. So we just get E to the 1 minus, now substitute the 20. The 20 is absorbed. So we get E to the negative 1. Just give us some practice with that, minus. Now we substitute the negative 20. Again, the 20 is absorbed, and we get E to the minus 1. Now we substitute the negative 20. The 20 is absorbed, but negative negative gives us a positive. So we have minus E to the 1. So that's just to give us some practice with the formulas. You could have used the evenness, but just a little practice, not too bad. So we get 10. So let's see here. Oh, and then we're going to get some 2's here. So let's go ahead and distribute these. So we have E to the 1, or just E, minus 1 over E. We'll go ahead and write that as 1 over E, if you like. And then we have another 1 over E, minus 1 over E. And then we have a minus minus, so we have plus an E. So actually, we're going to get another factor of 2, which kind of surprised me. So now we've got 10, 2 E's, minus 2 of the 1 over E's. So I just write that as 2 over E. But of course, we've got 2 in everything, which we can factor. So that would be a 20, 2 times a 10, E minus 1 over E. So that's the exact length of the inverted quaternary right here. That's this length right there. So as I said before, compute the length here and then multiply by the breadth to get the area of the roof. So now we did the hard part, which again, just reviewing hyperbolics, and you don't teach this problem unless you give your students all the rudiments, and you just wave your hands over it. It's a waste of time. So this implies that roof area is now, we just say 100 times the arc length. So 100 times S, and that will be 100 times 20 times E minus 1 over E. So exactly that gives us 2,000 times E minus 1 over E. So sorry, I moved that up so you could see it. The calculation here, again, the hyperbolic functions are not meant to be torment. They're not meant to be torment to give you a hard time. They're simple functions when you consider how their differential equation derivation actually generates these exponentials. And so they're easy to manipulate. And plus, because you know the calculus of the natural exponential, you get the calculus for free. And then you can solve for the inverse trig functions or the inverse hyperbolic functions just using basic college algebra. So they're not as complicated as the regular trig functions, I don't think, but the same techniques ensue because you get all these nice identities that mimic the standard trig identity. So that's where students say, well, can I just do one or the other? But you're going to see these functions in your future work. So they're worth learning a little bit about. And since they're fairly simple, you could go down and write all of these down, and you can look in your ebook in chapter 5 where they have a nice treatise on the hyperbolic, and which is right after the inverse trig functions that we did. So feel free to look at that so you have a little bit of extra time just to ingest all of this. So now what I want to do, now that we have all of these curves, let's think about what we can do with some surface area. So there's a formula about the arc length of an asteroid, which you can look in your notes on Blackboard. I may just go ahead and do that next class. But I want to talk about how we could, for instance, if you thought about taking a curve and rotating it about an axis, not the region bounded or whatever we've done before, but just a curve. And if you rotate the curve about an axis, you generate a surface as opposed to a solid. You generate a surface. And you might say, well, with that construct, can we actually compute the area of the surface? Like, okay, well, that's a surface of revolution. Like, we can say, well, that's a solid of revolution. We can compute the volume. And the answer is yes. And in some cases, the integrals are actually easier because of the form of the integram. So we'll just say this: area for a surface of revolution. Area for a surface of revolution. So we're going to do this just like we did before. We're going to think about the frustum, and we're going to chop it up and then apply it to the rest of the integral. But it won't be nearly as hard because we're going to use the area formula for a frustum, which you could actually derive if you wanted. So here we go. Let's take an axis of revolution. And we're gonna draw in the, what is it called, the waste paper basket, so to speak. Let's see, we'll go up to here. Always draw some points so your figure will look decent, maybe. So this is when you think of the standard waste paper basket, even though now they're all shapes. But you basically have a right circular cone which you've truncated. And so the result is what we call a frustum. 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 Okay. And the frustum has a slant height, which we call L. It has a smaller radius, which we'll just call R1, and a larger radius, which we can call R2. And the area of the frustum, this, it's not hard, well, it's not simple to derive, but it's you could do it. The area of frustum. And this is what we use to motivate the integral definition of surface area, or area for a surface of revolution, is going to be 2 pi LR, where, and this is the thing, where R is the average radius. We've seen this before. R1 plus R2 over 2. That is average radius. So the idea is what we want to do, and this makes it simple. This basically will give us the element of arc length. Element of arc length, like a slant height. And the average radius here will be the distance to the axis of revolution. Now you can spend a whole lot more time with this, but that's really not what's important. So now what you can do is, now if you think of a curve, say something like this, where we break it up, x sub I minus 1, x sub I, you'll think about a element of arc length here. So we'll just say, let me start it here. The element of arc length, this will be your delta S, which will sub for the slant height, so to speak. And then your distance to the axis of revolution. So we can say this and say distance to axis of revolution. Now, we'll do this for every element of the partition. So in this case, the partition can start at A, x sub 0, x1, x sub I minus 1, x sub I, 2, x sub n. Of course, we can use the intermediate value theorem and put a little bit more rigor into this, but basically we're just using this area formula. So we do this area calculation here, where we take the product of 2 pi, the distance to the axis of revolution, and the element of arc length, the slant height, and do it for each subinterval. So this implies, this is where we say area, we use the uppercase S, will be the limit as the norm goes to 0. So we have the sum, I equals 1 to n, and so we just fill it in, 2 pi. And then, of course, we can call the actual curve here, just to make it simple, we can call this y of x. So we have the element of arc length. So this will be 1 plus y of x sub I. Well, let's just say in this case, we'll just use anything, any element. We'll do c sub I, because any element in the subinterval there will work, squared, 1/2. And then, of course, we'll have the distance to the axis of revolution, so r sub I, c sub I, and then the delta x sub I from the element of arc length. So the idea here is that these two numbers don't necessarily have to be the same. In the limit, everything will work out to the definition of the Riemann integral. So this could actually be another element in this subinterval. So it doesn't necessarily have to coincide with that, but it's okay. And so now in the limit, we get 2 pi, which we can factor, integral AB, and we can write the distance to the axis of revolution first, and then the element of arc length. So the idea here is that we can actually get a formula for the area of the surface of revolution using the arc length with the frustum as the geometric foundation. So we think we can create a frustum by revolving this particular curve about this axis. So when we revolve, we generate the frustum. So what we're thinking of is, let's just use the geometry of the frustum to generate a frustum here. Okay, generate a frustum and do that for each subinterval. And each time we're basically adding the area of the frustum using this formula, which we have right here for each subinterval. And so basically, when we look at the area of the frustum, we see that same formula in the integral, just like we have for the shell method or the disk method or washer method. So what I want you to see here is that you have a very simple rendering of an area for a surface of revolution just by adding the distance to the axis of revolution, which is basically the average radius. So the idea here is that we don't have to start from scratch. We can use the idea of arc length and then the concept of the frustum geometry to define the area of a surface of revolution. So now, and I'll put the big S here, this formula is easy to remember as long as you just think arc length, 2 pi, distance to axis of revolution. So you can put these formulas on note cards so you can have them readily available. So that's a nice formula. So let's look at how we could actually use it. So now we're thinking, will this make the integral easier? And in most cases, the answer is yes, because then with that extra algebra there, you don't have to rely upon the square root so much. And usually you can do a calculus 1 integral that marches on much easier than the more difficult integrals that we did for arc length. So it's nice to have a formulation that usually will make the work easier. So let's look at an example, and I'll show you some tricks with this. We'll start out with one that's fairly straightforward, and then maybe next lecture when we do the work problems, I'll do some additional ones. Let me adjust the chair here. There we go. So let's look at this following one. Just do a very straightforward calculation. A college algebra curve. So it says revolve the curve. So now it looks like we're doing college algebra, square root of x times 2, where x lives between 4 and 9, about the x-axis. And you can be very creative here. You can use independent variables that make the problem easier. You're not always tied to a particular independent variable if you can work the algebra to get that distance to the axis of revolution legitimately. So there's some ease with this type of computation. And then it says compute area of surface of revolution. So always think about the frustum. That's our springboard with the geometry. So now, if you like, we can go ahead and make a nice little sketch just to kind of organize our thoughts. So now we've got what, 4 to 9. So we can just mark this off, 4, 9. And of course, this will give us a 2 and a 3. I'll spread this out a little bit more so we can see the curve. So I should label first and then, draw it, then label later. There we go. So got to get that vertical tangent there, which I don't really have. Let me label this last so I can get in my vertical tangent. I don't like the curve to look incorrect. So let me get the vertical tangent here. There we go. And now I'll do the labeling after the fact, so to speak. And then the 3 about up here. And then, of course, in all of these, I'm going to multiply it by 2. So that'll give us a 6. And multiply by 2. And that'll give us a 4. since the curve is, in this particular case, 2 root x. So we have square root of 4, which is 2. 2 times 2 is 4. Square root of 9 is 3. 2 times 3 is 6. So that gives us what we need. So here is the, and I'll kind of outline this. This is our curve. And so now we have x lives between 4 and 9. So we can take an x, a representative x, and then an element of arc length. So this will just be our delta S sub I. And then, of course, we can look at the distance to the axis of revolution. So if you like, we don't necessarily even have to use the I. We can just think of that as the element of arc length, just delta S. And then the R will just be the definition of the function from the x-axis to the function. And then, of course, revolution here. So we have 2 square root x. So that at least gives us all of the ideas about the frustum as far as the distance to the revolution axis. Now we do the arc length part. So at this point, we just go here. Let's go ahead and write y as 2x to the 1/2. And so now y prime will be 2 times 1/2 x to the negative 1/2. So this just gives us the 2's absorbed. So this is x to the negative 1/2, or just 1 over the square root of x. And now we form the 1 plus y prime squared. So now 1 plus y prime squared will be 1 plus 1 square root x quantity squared. And of course, the square will retire the square root of x. So this gives us 1 plus 1 over x. And since we have this form here, let's go ahead and get a common denominator. That'll make the algebra a little bit easier. So we'll have a common denominator of x plus 1. So that gives us this quantity. And so now, by definition, S, the area of the surface of revolution, will now be 2 pi, integral in this case, 4 to 9. And now we can go ahead and write it in. The distance to the axis of revolution, 2 square root x. And then we want the element of arc length. So we have the square root of this dx. So we have times the square root of x plus 1 over x dx. So again, r and this could just be written ds for element of arc length. So we use delta s here, and then in the limit, we use ds. So this is element of arc length, distance to the axis of revolution. And now, of course, this algebra is easier than we've done in all the problems so far today. We've had tedious algebra to do, and this is the first time it's actually been simple. So now 2 pi, 4 to 9. And if you like, you can go ahead and, let's just go ahead and remove that 2. That's just in the way. So we have 2 times right there. And now we have the square root of x. And now we can apply the laws of exponents, of course, where this is well defined. So we get the square root of x plus 1 divided by the square root of x. So, you know, we do so much college algebra and trig in this class that it's like we're in pre-cal again. And it truly is. We spend more time with the algebra and trig than we do the actual calculus, but that's kind of the nature of what we're doing. So now this gives us 4 pi integral 4 to 9. And now the square roots absorb, and we get the square root of x plus 1 dx. And now, when you think about this particular problem, it's like, where was this example when we were doing those horrible fractions and we were doing hyperbolics and we were doing, you know, the integral of secant? I mean, really, you're thinking this is really much simpler. And so in many cases, you'll see that the utilization of the distance to the axis of revolution will simplify things. So now we can write this in a way that's a little bit more user-friendly. So 4 to 9, x plus 1 to the 1/2 dx. And so now add 1, divide by the new power. Of course, u equals x plus 1, du is dx, so this is definitely table ready. So we get 4 pi. The new power will be 3/2, so we divide by that, so that's multiplication by 2/3, x plus 1 to the 3/2, integrate from 4 to 9. So now, of course, the 2 times the 4 will give us 8, so we get 8 pi over 3. And now we substitute the 9, so that'll be a 9 plus a 1, so that's a 10 to the 3/2. And then we substitute the 4. 4 plus 1 is a 5, so very simple. And now, if you like, and this is your choice, it's customary to do the 3/2 power is 10 times square root of 10. That's just a customary thing, but certainly this is fine. But if you want, you'll see it written this way in many textbooks. So this will just be 10 times the square root of 10. This calculation occurs a lot in Calculus 3 too, when you're doing these types of calculations, because the surface area or the area of a surface of revolution will pass on into Calculus 3, and then you'll do parameterizations of surfaces and things, and all of this will just come full circle. And then we have 5 root 5. So now you can see that what we basically do here, you know, when you think about this is like a thimble, but there's no cover to it. You get a hoop. So this is more like a rounded waste paper basket. So when you think about the types of calculations that you do, we'll do some more. You can take curves that are more standard to you, that you learned in college algebra, like we have the square root function, and then you're like, wow, you know, surface area or area of a surface of revolution is not usually as tedious. So again, I think what I'll do next class, I may add another example of this, but what's nice about the area is that again, the formulation is just much simpler. You still have to do the element of arc length. And that just takes the certain amount of algebra that you have to do. But notice here, since we have a much simpler function, this was easier, okay? So as you work through these examples, again, focus on how we set up the formulas and practice writing them down. Just write them down. You can write in any variable you like. And then do some examples, work through the problems in our lecture. Also go to the lecture notes on Blackboard, which are other lecture notes that I've used before, and also the PowerPoints. Lots of times the PowerPoints are really very useful because they have nice summaries of everything that I've taught you, and you can really make some nice note cards with those. And then of course, go to the practice test and see, you know, this is the kind of example that Professor Ron will test you on. So again, just remember that the arithmetic will ease. That is, as we get out of this chapter, after we do center of mass, we're going to start talking about more techniques of integration. So we won't be doing as much tedious arithmetic, but we will be doing a lot of calculus and algebra. So of course, the first time I say there's less arithmetic, we'll have a lot more. But as we work through the work problems and then the center of mass problems, they will be very similar to these calculations. But know, ladies and gentlemen, that these topics just like function transformations in college algebra are universal. You will use these over and over again, and you will generalize them in other courses. So this, as a future STEM, a lot of you future engineers and things, this ought to be kind of neat to you because you can make your own models. And again, as you take more classes in engineering, as you get to the university, you'll use your mathematics as a tool. So lots of the tools that you learn in this class will stay with you for the rest of your life. Okay, so I want to thank everybody for your attendance today. Like I said on Monday, I will get up some information about our first test. We always have a first test in the fourth week, and then I think your second test will come a little bit earlier to give you a little bit of a breather. But breather in Cal 2 is like a breather in pre-Cal. That it's not much of one. But I will have a conference hour today. I'll send out invitations for that. And then of course, tomorrow I have conference hours throughout the day. That's one of those days that seems to never end. So if you have questions, you want to stop by and ask about what you're working on, that'll be excellent. So I wish everybody well as you complete your homework and do your quizzes, and everybody have a great day. I'll see you soon.